This is the solution to the second problem on the magnetism free response packet. It's the second question on the 2007 exam. It says your research director has assigned you to set up the laboratory's mass spec so that the separate strontium ions have a net charge of plus 2e from a beam of fixed ions. The spectrometer above accelerates the beam of ions from rest through a potential difference E. After which the beam enters a region containing uniform magnetic field B of constant magnitude, perpendicular to the plane of the path of ions. The ions leave the mass spec at a distance x from the entrance points. You can manually change E. So here's the sketch of the apparatus. For starters, we can see that the beam of electrons enters the region. It's accelerated here by these plates. It leaves through that small gap and then negotiates here this arc of radius r. They want to know for question part A what the direction then is of the field, the magnetic field, to produce the trajectory shown. So first thing you should be thinking is right hand rule. So I'm going to use my right hand where my middle finger is going to be in the direction of the magnetic field, which we don't know, so I can't really use that part yet. My index finger, and I'm using my right hand because it's a positive charge, my index finger is initially going to be directed upwards, which is in the direction that the particle ends the magnetic field. And my thumb, I could orient in a bunch, either to the right or to the left, but I'm going to orient it to the left, and the reason is I know that there must be a force directed to the left since, let me erase that. There must be a force directed to the left because it's negotiating that circle there. So, you know, when I show the particle, it's got a velocity directed up, like so. Let me change that. The velocity is directed up, and the direction of the acceleration, and therefore the direction of the magnetic force, has to be to the left. And obviously that continues as it moves around the circle. So therefore, once I've done that, I can see that my middle finger would be directed into the paper. So the magnetic field here, the solution to part A, should be B. Yikes, sorry about that. My pen is behaving badly. The magnetic field is directed into the paper. Okay, so the next question then goes on to ask, the ions travel at constant speed around the circular path. Explain why the speed remains constant. If I go back to the sketch, you can see that if I additionally take some time to draw in the magnetic field, it's going into the paper, so I'll just draw that as x's here. So the magnetic field line is going into the paper. We can see that regardless of where that path is in the 2D plane defined by the paper. So let's take a look at this. The 2D plane defined by the paper. This is the x direction and this is the y direction. So wherever I am, and even if the particle is further along, in this case I'm going to draw it at some second position, let's call that B. The direction of velocity would be tangent to the circle. The direction of the magnetic field is into the paper, which is still 90 degrees to the direction of velocity, which means that there still is going to be a full magnitude force directed towards the center of the circle, F sub B. And so because that is true, then we can say then that the speed remains constant. It's not accelerated by the magnetic force. So let me go ahead and write that out. We can say that F sub B is perpendicular to the magnetic field and the direction of velocity. And this does not change. So therefore, it doesn't change the magnitude of velocity. It only changes its direction. All right, so that's kind of my shorthand response to part B of that question. C then says, calculate the speed of the ions with charge plus 2e that exit at distance x. This is another kind of classic example of magnetic forces being centripetal forces in a mass spec. So you should kind of be used to seeing that kind of thing at this point. So I've got a magnetic force that is the centripetal force. I can say mv squared over r is equal to qvb sine theta, where of course sine theta is equal to 1 and does not change the value of any of these guys on the right hand side. I'm solving for v, so this v on the right goes away and one of the v's on the left goes away, which means I want to isolate this guy. So I'm going to multiply both sides by r and divide by m. My expression then turns into this. V is equal to q times b divided by m, and I need to remember to multiply both sides by r, so I get an expression that looks like that. QBr over m is equal to the speed of the ion. So now I can go ahead and just plug these things in. It is 2e, so that's the charge. It's going to be 2 times the fundamental charge, 1.6 times 10 to the negative 19 coulombs, thank you Robert Millikan, times the strength of the magnetic field, which was given to us in the initial conditions, which is 0.09 Tesla, and I'm going to multiply that by the radius, which is 1.75 meters, is 1.75 meters, and I got to remember to divide that by 2. If I go back up here to the data that was given to me, it says the exit distance x is 1.75 meters, so therefore this radius r is half of those 1.75 meters, which is why I plugged it into my calculator this way. And then I need to divide that all by the mass, which is 1.45 times 10 to the negative 25 kg. Again, that's given to me in the problem. And I get 1.74 times 10 to the 5th meters per second. And that's my solution for this part C of the problem. Part D then goes on to say, calculate the accelerating voltage E needed for the ions with charge 2e to attain the speed we calculated in part C. Again, this is something you'll see from time to time, so let's go ahead and take a look at this picture real quick. So when we look at the mass spec, we can see here that these plates and the accelerating difference in potential is required to give them an initial kinetic energies that when they enter the magnetic field region they have sufficient, or a known B I should say, sorry, a known V, a known speed. So it has to do with the voltage. Don't confuse, and this is easy for me to do, don't confuse V for voltage with V for velocity. So I'll use the cursive V for velocity. This should kind of harken back to problems we've done previously in electrostatics. So what I'm going to do is consider, as soon as I see kinetic energy and speed, I should be thinking of the work energy principle. So let's remember that by definition voltage is the potential energy per unit charge. And I can say that that's equal to the negative kinetic energy per unit charge. And of course I can expand this a whole bunch of times, but I'm going to stop here because I have what I need. That becomes negative 1/2 mv, where v is now velocity, that cursive v squared, over the charge. And I've got the relationship that I'm looking for. What am I looking for? Well, I'm looking for the accelerating voltage, which is what I have over here, v, and I've got it in terms of speed and charge and mass, which are all things that I have. So that really allows me to kind of, that's the form that I'm going to use. So I'm going to say that v now is equal to 1/2 mv squared over q. I need to multiply both sides by q, and that gives me 1/2 m velocity squared. Okay, so now that I have that, I'm ready to solve for v. So I'm just going to divide both sides by q, so that accelerating potential or voltage is going to be equal to mv squared, in this case velocity squared, over 2 times q. I just plugged the 1/2 in this way and divided by Q, and now I can substitute my numbers in for mass, 1.45 times 10 to the negative 25 kg. The speed we solved for previously, it's right at above 1.74 times 10 to the 5th meters per second. And I need to divide that by twice the charge, which in this case is going to be 2 times 1.6 times 10 to the negative 19, and that's going to be coulombs. And I made just a quick mistake here, and the reason is Q is 2 times E, so that I guess I can fix that by just saying that I need another 2 in front of this. So it's 2 times Q, which in this case is 2 times 1.6 times 10 to the negative 19. All right, so when I run that through my calculator, I get 6,860 volts is going to be the required accelerating potential in order for the mass spec to kind of work that way.